Hello, I am Andrew Stevens' avatar. The real Andy is a Doctor of Technology candidate at Purdue University and a year 2000 graduate of Perry Meridian High School. He has been helping coach a VEX IQ robotics team at Jeremiah Gray Elementary School in Perry Township, Indianapolis, Indiana. One of the required elements of VEX IQ competitions is an autonomous skills challenge, and I wanted to help teach our VEX IQ programmers how to approach this challenge. This video is generally for 4th to 6th grade students and will rely on using VEX Code Blocks. This video is an intermediate video, meaning that I expect viewers to already have some background in programming on VEX IQ's Blocks platform. Your first approach to autonomous coding may have been a linear string of functions, but I want to introduce you to the concept of breaking down small, repeatable actions into individual pieces and then calling those pieces as you need them. Throughout this example, I will demonstrate using VEX VR and a SwishBot from the 2024 to 25 season Rapid Relay. In the example above, you see 3 columns of code. The left column contains the action manager, which is the general code that is followed when the device begins to run. The middle column contains a loop function that manages the firing arm. This function keeps the arm down except when firing. The third column contains 2 event functions that turn the rotary grabber on and off as needed. In this example, SwishBot begins its journey with functions, the helpful assistants that take care of specific tasks. Think of an event-driven function like a robot helper who patiently waits to be told what to do. These helpers don't run all the time, they only spring into action when SwishBot sends out a special message called a broadcast. For example, SwishBot has a helper called startGrabber. You see this on the right at the top of the graphic. This function is responsible for spinning the intake motor, grabbing objects whenever it's needed. But it doesn't just start spinning on its own. It waits for SwishBot to send the startGrabber message. As soon as it hears the message, it jumps into action, starts the motor, and begins the grabbing process. There's also another helper, stopGrabber, which listens for the stopGrabber message. When it hears the call, it stops the motor, bringing the grabbing to a halt. These functions are smart because they let SwishBot call the same task repeatedly without rewriting the code. If SwishBot ever needs to tweak the grabber's behavior, like adding a sound before it spins or adding logic to look for feedback from a sensor, all it needs to do is update the function, and every time it's called, the change is already in place. Functions make SwishBot's life simpler and more efficient. But SwishBot doesn't just rely on event-driven functions. It also needs a system that can keep certain tasks running all the time. That's where the loop function comes in. A loop function is like a tireless worker, constantly checking conditions and responding to them as needed. For SwishBot, the loop function is called fire and reload, and it keeps the robot's catapult ready for action. The loop function, seen in the forever control, works by checking a variable named fire. A variable is like a memory box where SwishBot stores information. The fire variable tells the robot whether or not it should release the catapult. If fire is set to 1, the loop function knows it's time to fire. It releases the catapult, waits for a moment, and then resets fire to 0 so the catapult can reload. If fire is already 0, the loop function knows to keep the catapult in its ready position, lowering it until the next shot. This constant checking and responding is the magic of the loop function. Without it, the catapult wouldn't know what to do, and SwishBot wouldn't be able to stay ready for action. The loop function ensures that every part of the firing mechanism works smoothly, all without needing someone to press a button every time. At the top of it all is the action manager, the leader of SwishBot's program. The action manager is like the conductor of an orchestra, deciding when and where each part of the robot's code should play its role. When the program starts, the action manager springs into action, directing SwishBot to drive forward, turn, and prepare to fire. It also tells the grabber functions when to start and stop by broadcasting messages like startGrabber and stopGrabber. But the action manager doesn't do all the heavy lifting itself. Instead, it delegates tasks to the loop function and event-driven functions, letting them handle their specific jobs. This way, the action manager can focus on the big picture, making sure SwishBot completes its mission. Let's see this code in action. Remember, this is just a starting point. Coding takes a lot of trials to continuously improve our work. We call this testing, learning, and improving iteration. Don't expect this code to score a goal. It just moves the bot far enough away from the wall to function safely, turns, and fires. Here it goes. Now let's explore using a variable to direct a loop function. A variable is like a memory box for your robot. It stores information, like a number, that the robot can use later to make decisions. In our example, we'll use a variable called fire to control when the robot's catapult should fire. If fire is set to 1, the catapult will be released. If fire is set to 0, the catapult will stay in its resting position. To create this variable, start by clicking the orange Variables button in the VEX Blocks menu. Then click Make a Variable and type fire into the box. Once you've named the variable, click OK. Now you'll see an orange bubble-shaped block labeled Fire in the Variables menu. This is your variable, and you can drag it into your program to use it. Variables like fire can fit into round placeholders in other blocks, allowing the robot to use the value stored in the variable. For example, we'll use fire inside a math block to make decisions later. The first step is to set the variable at the beginning of your program so the robot knows its starting value. Drag a when started block onto your workspace. Then drag the set fire to block from the variables menu and place it underneath the when started block. Set fire to 0 to tell the robot that the catapult should start in a resting position. This step is critical because it gives the robot clear instructions about what fire should represent when the program begins. Next, we'll set up a system to check the fire variable continuously. Drag another when started block into your workspace. Below it, place a forever block from the control menu. The forever block will keep the robot checking the fire variable over and over for the entire program. Inside the forever block, drag an if-else block from the control menu. This block helps the robot make decisions by asking a question and choosing between two different actions based on the answer. The if-else block has a hexagon-shaped placeholder at the top. Go to the green operators menu and drag an equals block into the hexagon placeholder. Then from the variables menu, drag the fire block into the left side of the equals block. On the right side, type the number 1. Now the condition reads, if fire equals 1. This is how the robot will decide whether the catapult should fire or not. To complete the program, let's add the actions the robot will take based on the value of the fire variable. Under the if fire equals 1 inch section of the if-else block, drag a spin motion block from the motion menu. Set it to spin the catapult motor to release. This action tells the robot to fire the catapult. After this block, drag a wait block from the control menu and set it to 1 second. This gives the robot enough time to fully release the catapult before continuing. After the pause, go back to the variables menu and drag the set fire to block. Place it under the wait block and set fire to 0. This resets the variable so the robot knows the catapult has finished firing and is ready to reset. Now let's complete the else section. Drag another spin motion block from the motion menu and place it under the else part of the block. Set this block to spin the catapult motor to lower. This ensures the catapult stays in the ready position whenever the variable fire does not equal 1. With these blocks added, the robot now knows exactly what to do when the fire variable equals 1. Release the catapult, pause for 1 second, and reset the variable. If the fire variable does not equal 1, it will keep the catapult in the lowered position, ready for the next action. This program creates a smart and responsive system that controls the firing mechanism with precision. In this section, we explored how to use variables, like our example, fire, to control decisions in a VEX IQ program. A variable acts as a memory box, storing a value the robot can check and respond to. We began by creating the fire variable in the variables menu, setting its default value to 0 at the start of the program to ensure the robot knows its initial state. Using a forever block, we created a system to continuously monitor the variable and added an if-else block to check its value. The if-else block acts as a decision maker. It checks if fire equals 1 using an equals operator. If true, the robot spins the catapult motor to release, waits 1 second to ensure the action is complete, and resets fire to 0. If the if statement is false, the robot performs the else action, spinning the catapult motor to lower, keeping it ready for the next use. This combination of variables, operators, and logical blocks demonstrates how the robot can adapt its behavior based on changing conditions, creating a flexible and responsive system. Next, let's set up our commands for the robot to turn on and turn off the ball intake mechanism. For this bot, the ball intake mechanism is a rubber band beater with a single motor. In this example, we will rely on 2 event-driven functions to listen for the signal to do these actions, start and stop. To begin, we will drag a when I receive event block onto the workspace. I will right-click and hit Duplicate to create the second. Under the first event block, we will click on the down chevron, select New Message, and enter the new message name of Start Grabber, being sure to exclude spaces. I like to capitalize each new word so I can more easily read the text. For the second event, let's go ahead and create a new message called Stop Grabber. The actions for both of these are much simpler than our fire and release loop function, because these actions only run when the bot hears the command. For each of these, we will drag the appropriate motion function onto the workspace, one for spin and one for stop, and link them to the appropriate event. For spin, we will select the motor we want to spin and select its direction. Stop is simple, we just tell the bot what motor to stop. Now is a great time to add gray comment blocks to your code to remind you of each block's function. Before we program the Action Manager portion of this code, I want to remind you that VEX programming should be carried out by the youth teams. As such, I am only providing cursory instructions on how to approach programming autonomous activities. It will remain up to the teams to fine-tune and add additional controls to optimize the program. I will work to create some additional how-to programming guides teaching additional areas of programming that can be explored. But I will attempt not to show a complete program that would work in real life. As many adults may be watching this, you are able to help within the rules. The teams must always be present for hands-on work. In this case, this means that teams should be the ones writing the final code. In my opinion, this does not mean you cannot help. In fact, I have had to do some coding in this tutorial to be sure I understood what I was teaching the teams watching. I have been an amateur coder since the late 1980s, and I cannot remember ever having a complex piece of code work on first pass. I encourage parents and coaches to co-code, but allow the team members to be the final arbiters of what goes into the robot. For the Action Manager, we will assume that you have set up your device's brain appropriately. In my work with my son's robot, I found two issues that held our programming up for several hours. First, be sure to enable your gyro. For Gen 2 brains, be sure to select the Brain Internal from the Setup menu. Second, ensure your wheel size and gear ratio are set up correctly, and you pick what direction is forward on your robot. In early work with our BenchBot, I found that if you send the robot out backward first, the device becomes unable to correctly measure turns and it gets stuck in an infinite spin. Long story short, set forward as the direction you want the machine to move when starting. Remember, this doesn't have to be the same as when you are under manual control. Back to coding. Your robot will have to start in the same spot on the same side each time. For this example using VEX VR, we will use the default starting location. Prior to this, I measured, tested, and modified the distances to make the video quicker. We need the robot to start moving forward 400 millimeters and turn right 90 degrees. We will drag these two blocks from the drivetrain menu and set them up. Next, the bot needs to back up into scoring range. I found this to be another 400 millimeters to hit the lower goal. We will then set our fire variable to 1 to trigger the firing sequence. This first firing sequence is only repeated one time. The next series of actions will be repeated until the timer concludes. Because of this, we will use a loop control, also known as a repeat command, and set it to go 10 times. Our first step in the loop is to wait 2 seconds for the fire command to finish. Even though there is a 1-second wait in the fire function, that only affects actions in that function. We need to give the robot a moment to settle from the motion of the fire. This is also a good opportunity to highlight that the force of the fire action will cause a real-world robot to bounce. This introduces error. We will talk about error correction in a later video. Continuing our loop construction, we need the eBot to drive back to the loading zone, forward 400 millimeters, turn right 90 degrees, and back up 120 millimeters. Next, we will turn on the grabber and wait 2 seconds to allow the firing arm to finish reloading. We then need the bot to move forward 120 millimeters to pick the ball up and immediately turn left 90 degrees. We can shut the grabber off and drive in reverse 400 millimeters to the firing position and fire again. This portion of the loop will play out through the net of the autonomous activity. Let's watch.